Here is the second set of slides that I created to try to help you understand simple mirrors and lenses. This is set number 2, where we're going to discuss the positive focal length devices. So that includes the concave mirror and the convex lens. Those are the devices that have what we call a positive focal length. They are capable of forming real images, but they also can produce a virtual image. So things are a little tricky here. Remember, the negative F devices can only create virtual upright images. These can create both a real inverted image and an upright virtual image. So got to be careful. Okay, so you can read this. This is just the motivation behind the set of slides. Okay, let's go back and look at our equations. Our simple equations for thin spherical lenses and for spherical mirrors. We have magnification is the ratio of image height to object height. And remember, if the image is inverted, this HI is negative. So if it's upright, like a virtual image, this is positive. Now you have to negate DI and over DO, and this comes from similar triangles. If you look at the theory in a textbook, this relationship comes from similar triangles when you do ray tracings. Okay, now for the lens and mirror equation, we have 1 over the focal length is 1 over object distance plus 1 over image distance. And don't forget, in this video, we're discussing the positive focal length devices. Okay, let's continue. By the way, you could, refer to this chart if you're having trouble. For both concave mirrors and convex lenses, this is true. The only difference between them is the following. For a mirror, a real image will have to be on the same side as the object. And for a lens, it's on the opposite side as the object. Because look at how they work. How mirrors reflect light, lenses transmit light. So everything's kind of bass-ackwards, if you will, but all the rules are the same. So basically, here's how this works. If the object location is beyond twice the focal length, you're going to get an inverted real image. The first time we've seen a real image here. And if an image is real, it's always inverted, always true. And it's going to be reduced. The magnification is going to be less than 1. Okay, as you move toward 2F, the object's getting big. It's still real and inverted, but it's getting bigger and bigger and bigger. And right at 2F, that's a point of interest. Right at when DO is 2F, you still have a real inverted image, but the magnification is -1 because it's the same size. It's just that HI is negative because it's inverted. So you get basically the magnitude of the magnification is 1, but it's technically -1 because HI is negative. It's an inverted real image. Now, as the object moves closer to the lens, now we're between F and 2F. We're still in real object space. We get an inverted real image, but now the image is enlarged. See, it starts small, then it gets the same as the object, and then enlarged. And it's still a negative magnification because it's still inverted. Okay, now as we move, the object moves just across the focal point. It's getting bigger and bigger and bigger, but here, just inside the focal point, just inside of F, the image moves on the other side of the lens, and it's an upright virtual image, and it's going to be enlarged. Okay, so, and between the mirror and F, it's just upright and enlarged. Now let's see how this works. So I'm going to explain this with diagrams. It's much cleaner. Okay, now, once again, let's look at the math one more time. Okay, here's our equation that relates the focal length, the image distance, and object distance. We can solve for image distance, and let's see what happens. Now, in this case, F is positive. So the only way DI can be negative is if DO is greater than F. See, if DO is greater than F, this is going to be positive because this is in the denominator. But if DO is, that should be, that's wrong. If DO is less than F, that should say less than. Sorry, that's right there. You just need to put that less than F. I'll fix it. That should be less than F. If DO is less than F, then this becomes negative, and you have a virtual upright image. Okay. Now let's go on. Now you can read this slide. Well, let's look at it. The only difference between the two optical elements is the location of the image. Remember, object rays undergo reflection on a mirror, whereas object rays undergo refraction in lenses. So For mirrors, real inverted images are on the same side of the mirror as the object. For lenses, real inverted images are on the opposite side of the mirror as object. See how that works? And for now, if your object is inside the focal length, that's when you get these virtual upright images. But for a mirror, they're on the opposite side of the mirror as the object. And for a lens, they're on the same side of the mirror as the object. Okay, let's look at that for these little cartoons here. Now, here's this is not hard to understand. Okay, so we're going to start over here where DO, the object distance, is like infinity. What does that mean again? We talked about this in the last set of slides. When DO is much, much greater than F, we're basically assuming that the object distance is huge, like approaching infinity. So if you have a little yellow arrow here, as you go to infinity, you're going to start off with an image basically right on this side of the focal length, right there, a little bitty object, a little bitty image that's inverted, just tiny. Now, as you move this way in this yellow rectangle, see that yellow rectangle? We'll call that, you'll see why in a minute. We're going to call that object space A. As we move this way, like this, the image starts off, they're real, inverted, and they're reduced. See that? They move this way, like that. So as you move this way, with the object, the image goes like this. Now, right at 2F, you get a real inverted image that's the same size as the object. Right at 2F, right at C, that's 2F for a mirror. See that? That's where your magnification's 1. Now, as you go across 2F, or that's C for a mirror, the center of curvature, or the radius, as you move in this object space right here between 2F and F, see that right there? You're going to go this way. And now you have enlarged. They're still real because they're inverted and real images. But so as you move in this little rectangle here, you're mapping out this massive image space, but it's still real. That's how you enlarge an image. Now, watch what happens now. Right as you move across the focal length, this image like flips at infinity and goes over to the other side of the mirror and starts here. So when you're right here with an object, you're right here with an image. And then as you move this way, like that, as the object approaches the mirror, the image approaches the mirror over here. And notice that it's always enlarged. See how big it is way up here? It's always upright, and this is negative DI space. See, this is a negative DI space for a mirror. See that? This is positive DI space. DI is positive over here. DI is negative over here. Magnifications are negative because the image is flipped. The magnification is less than 1 here, the magnitude. They're reduced images, enlarged images, but they're negative because the magnification, because HI is flipped, it's upside down, right? So the magnifications are negative. Here the magnifications are positive. Okay, and there's all your math. You can look at that. You can look at this. Make sense of it. Okay, let's look at the lens. Same thing, except what? What's going to happen in the lens? These spaces are on the other side, right? Because lenses work by what? By refraction. So let's start with the same idea. Here's your lens. And here we're going to start again at infinity. Our object is at infinity, or way, 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 way far away from the lens. Like this distance is much, much greater than F. So this really isn't to scale, right? This rectangle would be huge. We need to keep extending way out here. Now, so as we start at infinity, or way far away from the lens, we're going to get a teeny tiny little object right here. An image, an inverted image right here near the focal point. And as we move, now see, remember for a mirror, it was over here. Okay, as we move this way in object space, this yellow rectangle, see how it grows? Just like that. So as we move black arrow to black arrow, we're going to map out this real and reduced image space. So DI is positive over here for a lens. See that? It's the same thing as a mirror, except for a mirror, that space was over here. See that? Okay, so we map this rectangle to this image space. So between infinity and 2F, we have real reduced images. Okay, now as we map out this little rectangle in object space over here, that's what OS stands for, object space. Right here between 2F and F, we get this huge, not really a triangle, but like a, four-sided figure that's got, this kind of like a triangle with on top of a rectangle, right? But anyway, we're going to map out this space here. So as we move this way, this image is going to move this way. And notice that it's still inverted, it's real, And these are magnified or enlarged. So here they're reduced images, and here they're enlarged images. And notice, once again, right at 2f, we got a magnification of -1. Same size, it's just inverted. Now, this is what happens. This is cool. As we move across the focal point, what happens? Right here, you've got this monster huge image, like say at infinity. Right as you go across f, this image flips and moves over here. Now, this is virtual image space. And as you move from here, from just inside f to the lens, your image is going to march this way. And this is a negative di, right? So this would be a image space for a virtual image space for a lens. Notice that we have negative di over here and positive di's over here. Remember, for the mirror, it's bass-ackwards. You've got your positive di's on the same side and the negative di on the opposite, right? Because lenses work by reflection. Lenses work by refraction and mirrors work by reflection. So I hope that really helps you understand this. I mean, it's kind of complicated, but it's worth it, because once you get it, you got it, and it's over with. Have a nice day.